So in this video I want to show yet another variant of these multiple caustic Poncelet constructions. I'm starting from a point P1 on an outer black circle, and I'm going to be using three caustics, red, green, and orange, in round robin fashion. Now these three caustics, they happen to be centered at 01, 02, 03, which are vertices of an equilateral triangle, this gray equilateral here, whose circumcircle, this dash gray circle, is concentric with the black. So I can actually play the game, right? I can execute a few iterations and see where that leads me. But actually what's germane to this video here is, let's go back to a single chord, is I want to take this to the limit and bring the radii of these three circles to zero, to nearly zero. Okay, so let's manually make these radii be nearly zero, something like that. I cannot make it quite zero because then I can't compute tangents, but let's pretend this is an approximation, and the tangent now just becomes a line that goes through 01, and then it's going to go through 02 and through 03. And what's going to happen to a system when I repeat this? So now I'm going through 01 again, through 02 again, 03 again, and so forth and so on. Do I ever come back to P1? Looks like I just did, right? So this was initialized in such a setting that I had found numerically before, where after 9 iterations of visitation of 01, 02, 03 in round robin fashion, I go back to P1. And interestingly, if I now move P1 on the circle, I get a quasi-porism. So I'm actually reporting the error here. It's of the order of 10 to the minus 7 error squared. That means that the distance between the first and 10th vertex is remaining, 10 to the minus 8, 10 to the minus 7. This could be further optimized, but it's within 1/10,000. Okay, you have to take the square root of that, of the circumradius, which is equal to 1. So again, I'm getting this phenomenon of a quasi-porism, and I found that indeed, if you actually look for multiples of 3, so here's an n equals 12 quasi-porism, you can actually change the circumradius of the equilateral to find different quasi-porisms, and they're all happening when n is a multiple of 3. So here's n equals 12, here's n equals 15, quasi-porism. I'm reporting the error up here. You can see that it remains pretty small. Here's n equals 18. What do I mean by quasi-porism? I'm actually looking at P1 here, and I can tell that this trajectory returns to P1. You can see there's a little bit of a deviation there. You see that the 19th vertex is not quite on top of P1, so let's see if we can adjust this manually and improve that. So I'm going to play with this setting here. Let's see if this thing is sensitive to this setting. Oh, I have to actually put this on free. So let's make this be 2. Yeah, that was too much. 1. Yeah, that looks better. So what if I now go through my porism? Let's see what happens. Yeah, this is better. So I did a little manual adjustment. And you can see here that my error squared is within 10 to the minus 9, 0, 10 to the minus 10. Okay? The jury is still out if I can actually zero this guy out perfectly, or this is always a quasi-porism. Okay? Experimentally, I would hazard to say this can never be completely zeroed out everywhere, but it can be brought to be at an average of 10 to the minus 9 square error, meaning 10 to the minus 3 or 10 to the minus 4 error over the circumradius. So this is 18. I still have over here, I believe, 21, which is also a quasi-porism. So I'm always looking for P1. So here's P1, and I want to know in this case if P22 is staying within P1 in a stable way. So I'm just looking at P1 here visually, and it looks like, yes, I'm keeping this quasi-porism throughout. And then finally I have 24. Maybe 24 is not going to work. There seems to be a problem here. And I'm just going to leave you guys at that. Looks like Mathematica has frozen. And again, this is a curious phenomenon, a quasi-poristic phenomenon. involving these passages through vertices of a central equilateral for multiples of 3. Okay, so Mathematica now bombed, and this is a good time to stop this video. See you on the next one.